The last thing we're going to talk about in this chapter and in this unit as a whole is section 3.6, where what we're going to look at is a pair of things that don't seem like they would naturally go together, but we're going to show have some really close and important connections. What we're going to see are how to handle negating conditional statements, as well as how to find something called the Morgan's laws. Which should sound familiar, because we saw De Morgan's laws for sets at the end of chapter 2, and I've been saying that there are a lot of connections between set theory and symbolic logic, not least of them being that they look very similar notationally. So hopefully, without doing anything in terms of showing that stuff just yet, you should have some sense of the flavor we're going to be shooting for with this. But anyway, first thing we're going to see is how to deal with negating conditional statements. Now let's start with the general statements P and Q up here, and I've already rewritten the truth table for dealing with a simple conditional. Now, when we're thinking about negating something like an if-then statement, we saw that the contrapositive gets close to the same place, but that doesn't really feel like a negation, and especially because a negation should have the opposite truth value, and things like the converse and the inverse, they were true some of the time and false others, so it doesn't really make sense to throw either of them in there. But let's think about what this would look like. So if we want to negate something, what we want to do is just flip its truth values over. So if we want to negate if P then Q, well, we just have to flip all the pieces. Get false, true, false, false. And hopefully, seeing that we're negating the pieces, you might get the sense that you want to negate at least one of the parts. So, let's see, maybe if we negate P, something will emerge. Well, if we negate P, then we get false, false, true, true. It doesn't seem like it ends anywhere close to this, because you want this second one to be true, and in that case, you would need something else that's true there. So maybe we'll try negating Q next and see what happens. We're just trying to work our way through some of our options here. If we negate Q, then we get false, true, false, true, which gets us a little bit closer, maybe. Because if you look at these two together, you take their disjunction, you get something that's true. Or if you looked at this one implying that one, you get something that's true. But conditional fails here, and a disjunction would fail in both of those cases. So neither of those options work, and if you think about a biconditional, well, that clearly fails down here too. So the only thing left would be thinking about a conjunction, and that actually makes sense if you look at this truth table, because conjunctions are the only things we saw where 3 out of the 4 options were false with 2 component pieces. So looking at that, think, okay, we probably want to take a conjunction, and we want a conjunction where both options in the second case, in the second row here, are true, and everything else is false. So looking at all of our pieces here, there's actually only 3 times where that second one's true. Not Q, and not P, or an original P. And then we can check our other cases to make sure that works the way it's supposed to. Well, true and false is false. False and false is false, and false and true is also false. So actually we found what we need. That is, if we want to take our conditional statement if P then Q and negate it, what we would get is equivalent to the statement P and not Q. That is, the negation of a conditional becomes a conjunction between the antecedent and the negation of the consequent. And we'll look at an example of how we can work with this next.